So this video is all about solving one-step equations by using a process that we call balancing. Now before we get to that, we have to go through a few different other vocabulary terms that we've learned in the last few lessons or previously when you've been working with math. The first is that an equation is what happens when you put two expressions together and connect them by an equal sign. Those expressions could be things like x plus 17 and 12 to create the equation x plus 17 equals 12. It could be 3x plus 1 equals 16. It could be 3x is equal to 21. Any time where you have an equal sign and you have an expression on the left and an expression on the right that are set equal to each other, you get what's called an equation. And when we were talking about solving equations with mental math, we reviewed the fact that the equal sign can have a whole lot of different meanings, but when it comes to an equation, it means that the left side and the right side are truly identically equal in value. The value on the left is equal to the value on the right. And because we have that restriction there, and it's very important when it comes to equations, we can find a value of the variable that makes the equation true. And to do that means to find the solution of the equation. So go ahead, pause the video, make sure you have written down somewhere the equation formed when two expressions are set equal to each other, and the definition of solution. Come back when you are ready to move on. So let's take a look at an equation that we will probably be able to solve mentally, x plus 12 equals 17, and use that as the basis for talking about balancing the equation and showing the work that we need to prove that we have in fact maintained that balance that is created by the equal sign. And so when we're solving in equations, there are two things that we need to keep in mind. The first, of course, is that we want to find a value for the variable, and that process is called isolating the variable. We don't want an equation when we start out. We have one that says x plus 12 is equal to 17. We really want that to look like x equals something, because that will show us what the value for the variable has to be. In this case, we can do it mentally. We can think what number plus 12 is equal to 17. Well, 17 minus 12 is 5, so therefore x must be equal to 5. That is what we call isolating the variable. Now, there are a few other different things that go along with isolating the variable when we get to some more complicated equations, but for the one-step equations we're talking about now, that's as far as we need to go with that idea. The second is that we want to do the work that shows that both sides of the equation remain in balance the entire time. For example, if we take 12 away from 17 on one side, we are suddenly seriously imbalancing the equation because the value of one has been changed without changing the value of the other. So we need to show that we are keeping the equation in balance. And that primarily drives everything we're going to do with work. And so one of the things that's true about equations, including the equation x plus 12 equals 17, is that we can add or subtract anything we want from one side of this scale as long as we do the exact same thing on the other side. So if you imagine that you have weights on this scale here, and you decide you wanted to add 15 pounds to the left side, well, you can keep the scale in balance by adding 15 pounds to the right side too. Similarly, after you've added those 15, if you wanted to take 12 away from the right, you could maintain the balance in that scale by taking 12 away from the left. The most important thing about what we do to show that we are keeping the equation in balance is to make sure that what happens on one side also happens on the other. Essentially, that what we add or subtract to one side of the equation, as long as the same thing happens to the other, we do not change the solution of the equation. And that's really what we're after when we're solving an equation, is finding a way of manipulating it so that we end up with an x equals something kind of solution, at least for the equations that we're solving, without changing what that solution is. Similarly, we can do the same things with multiplication and division on both sides of the equation. So in the equation 12 times x is equal to negative 144, we could manipulate both sides of the equation not only by addition and subtracting, but perhaps by multiplying it by 3, as long as it happens on both sides, or perhaps dividing it by 7, as long as that happens on both sides of the equation. And that's something that you might have guessed we call the multiplication and division property of equality. Multiplying or dividing the same non-zero, very important, non-zero amount from each side of the equation produces what we call, again, an equivalent equation. One where the solution is the same, but we've changed the form of the equation. So I'm going to ask you to pause the video, write down these two properties, because they are the deep mathematical properties that allow us to do this. Unpause the video when you're ready to move from this one to the next one, and then we'll get into some example problems of how we show that we're keeping the equation in balance. Okay, moving on now to the multiplication and division property. Very important, it must be the same non-zero amount in this property. Pause the video, write this down, come back when you're ready to move on. So let's take a quick look at that equation that we had before, x plus 12 equals 17. Now what we know about equations is that we can add, subtract, multiply, and divide on both sides of the equation, and our goal is to go from x plus 12 to x. And so we're going to look for the inverse operations of everything that is wrapped up in the x. The 17 off on the right-hand side, that is important because it's going to help us end up at the correct value for this solution. But what we're more interested in is this plus 12 here. The plus 12 is what's getting in our way of having just x. So when we look at x increased by 12, the way to walk back, if you will, adding by 12, is to do the inverse, subtracting by 12. So because we see addition here, x is being added to a number, we're going to subtract the number away from the left-hand side. That's going to leave us with just the x. That is the isolating the variable step in solving an equation. Now on the right-hand side, 17 minus 12, that's 5. And so that is one of our processes for solving equations. If we see addition wrapped up with the x, we're going to do subtraction. This step right here, being circled in yellow, that's the step. That's the most important one that we do because that's the one that shows that we keep our equation in balance. And this is going to be the focus of all of the equation work that we do, is how to use that work to solve an equation. Similarly, if we have an equation like x minus 12 is equal to negative 5, what we see wrapped up with the x is subtraction. And so if we're going to invert subtraction so that we go from x minus 12 down to x, we're going to add 12 on both sides. Again, it has to be on both sides, and we have to show that step of work because that's where the balance comes in. Now, the minus 12 plus 12 cancel each other out, so we end up with just an x. Negative 5 plus 12, and we have to read it that way, top to bottom, negative 5 plus 12 is 7. So our solution for this equation is x equals 7. Looking at multiplication now, we have a few different types of notation things that are important when we get to multiplying and dividing in equations. 7 times x is equal to negative 56. Well, as in addition and subtraction, we use the familiar operation symbols, the plus sign for addition and the minus sign for subtraction. When we are dealing with multiplication and division, in this case, we want to divide by 7. But instead of showing the division sign, we're going to show it over a fraction bar. That is our strong preference mathematically when we're solving equations or even working with equations that involve division, is to show them using a fraction bar rather than a division sign. That way, the times 7 divided by 7, that cancels out. Negative 56 divided by 7 is negative 8. Remember that that process is the most important one. We are dividing by 7 to get rid of the 7 times x and make it just an x. And then on the right-hand side, we end up calculating negative 56 divided by 7 to end up at the value for our solution, which is negative 8. Similarly, if we have division in an equation, we're going to be very careful with the way that we write it. It would be tempting, potentially, because this is division. We know we need to use multiplication to write a times 5 underneath there. But that's problematic for 2 reasons. First is that we already have an x, or a variable, in the equation, so we really can't use x as a multiplication sign anymore. And the second thing is when you put the 5 below the division sign there, it almost looks like you're trying to write 5 times 5 at that point in the equation. And that can get potentially confusing if we're dealing with more complicated equations than just the ones that we have. So instead of writing it on the bottom of the equation like we have for other things, we're going to write it on the side. Now, times 5 divided by 5 will cancel out. We can see that with the multiplication there. And 5 times 0.75 is going to be 3.75. So those are the example problems. Got 2 pages of practice problems for you, one with addition and subtraction, one with multiplication and division. Let's go ahead, pause the video, solve these equations. Make sure you're showing your balance work. Come back when you're ready to move on. Now in the upper left-hand corner, we have two possibilities. We're adding a negative 5 here, which means that we could subtract a negative 5 from both sides. That would invert the operation. We have an x. Negative 5 minus negative 5 becomes negative 5 plus 5, because minus a negative is the same as plus a positive, which gives you 0. So that is one way we could look at that work. Alternatively, we know that adding negative 5 is about the same as subtracting 5, so let's just add 5 back to both sides in any case. Either way, we end up at the same solution. On the right-hand side, we have x minus 12. And the upper right-hand side, the inverse of subtraction is addition. That's going to cancel the 12 from the left-hand side, and we're going to give us 16 plus 12 is 28 as our solution value. Down in the lower left, we see x plus 15. To remove the plus 15, we're going to invert the operation, minus 15. Always inverting the operation, never inverting the sign. Negative 4 minus 15 is negative 19. And in the lower right-hand corner, we have x minus 9 is equal to negative 5. We're going to add 9 to both sides and end up with x is equal to 4. So that's the first set of practice problems. Remember, again, the most important step that we have is this balancing step right here. So as you're working on it, make sure you are showing that type of balancing. Last page for you, 4 practice problems, 2 with multiplication, 2 with division, and then pause the video, solve them, and come back when you're ready to move on. In the upper left-hand corner, we have 17 times x. That means we need to divide by 17. We get x is equal to 19 because 323 divided by 17 is equal to 19. Again, make sure that you are showing division using the fraction bar rather than the division sign. In the lower left-hand corner, let's just go down and finish off multiplication here before we move to division. We have negative 0.6 times x. That is not a subtraction sign because there's nothing that's in front of the sign for it to be subtracted from. That's in fact a negative number times x. That means when we divide, we're going to need to divide by that negative number. We're not going to change the sign for it. We're just going to invert the operation. 1.8 divided by 0.6 is 3. So positive divided by negative is negative 3. Over on the upper right-hand side, we have x divided by negative 3. We'll multiply it by negative 3, again, on the side rather than below. That way we can see that fraction multiplication that cancels it there. 11 times negative 3 is, of course, negative 33. And then down in the lower right-hand corner, we put a division sign here just so you could see the operation in a different way. Going to multiply by 4 on both sides. On the left-hand side, we end up with x. On the right-hand side, we end up with 4/16 or 1 over 4. So that's it. That's solving equations. Most important part is we need to show the balance work, because the two things that we're after when solving equations are A, isolating the variable, and B, making sure that we have shown the appropriate work to keep the equation in balance.